So, by now we have already learned how the oxide growth takes place and the kinetics of oxide growth. Now, we will discuss some of the results based on the kinetics of oxide growth. That means the dry oxidation and wet oxidation, in both cases, in dry oxidation the oxidation species is the oxygen only, and wet oxidation species are oxygen and H2O molecules. So obviously, since species are different, and for those cases the parabolic rate constant and linear rate constant, that means B by A is the linear rate constant and B is the parabolic rate constant, those values are different for different growth conditions. And third one oxidation is the pyrogenic oxidation, we know, and pyrogenic oxidation is basically wet oxidation, but its quality will be good because the pyrogenic steam we are getting from the oxygen and hydrogen. So that's why pyrogenic steam prefers in industries, because it will produce very good quality, high quality oxide film. And there the oxidation kinetics we got from oxidation kinetics, we got certain relations, and based on the relations we can find the oxide thickness at a particular temperature at a particular time. And this curve here, it shows the thickness, oxide thickness for different times when the oxidation is taking place at 900 degrees centigrade. And you can get some other informations in this particular view graph. For example, you have seen that the oxide thickness versus oxidation time is shown for different ambient pressure. That means if you do the oxidation at 1 atmospheric pressure, and if you do the oxidation under the same condition, means at same temperature and same time, but if you do the oxidation at 20 atmospheric pressure, the oxide thickness is very large. For example, here is a 1 hour time. In 1 hour, if 1 atmospheric pressure, you are getting about 0.2 micron oxide thickness. But the same thing, if you go for do at 20 atmospheric pressure, then oxide thickness is roughly 1.8 micron. That means you see here it is a 0.2 to 1.8. That means 9 times more. If you increase the pressure inside the oxidation chamber from 1 atmosphere to the 20 atmosphere. There are values available in between also, 5 atmosphere, 10 atmosphere. That means high pressure oxidation gives higher thickness at the same time and the same temperature. Higher thickness of what? Silicon dioxide. At the same time, same temperature. And another point also is to be noted from this result, that in all curves, that is 1 atmosphere or 5 atmosphere or 10 or 20, both the oxidation growth rate is shown or oxide thickness is shown both for 100 orientation substrate and 111 orientation substrate. In 1 atmosphere, the lower curve is 100 and the upper curve is 111. In all high pressure oxidations also we have seen that the oxide thickness in 111 oriented silicon substrate is more compared to 100 orientation silicon substrate. That means the oxide growth mechanism is different. It depends on the crystallographic orientation of the silicon substrate. The silicon substrate, basic substrate, what you are using, normally it may be either 100 or 111 orientation. That means there is an effect of growth rate on crystallographic orientation. That we will discuss little bit in detail in the next slide. Next, view graph. You can two view graphs are shown here in this slide. So there one is again oxide thickness versus temperature. For the same time is fixed here 60 minutes. Time is constant 60 minutes, and you are increasing temperature from 700, 800, so 900 to 1000 degrees centigrade, and also at different atmospheric pressure. 1 atmosphere pressure here, this is I think 5, then 10, then 20. So here also we can notice that if the temperature increases, the oxide thickness also increases. Whatever may be the ambient pressure in the oxidation chamber, if the oxidation temperature increases, oxide thickness increases. Right? In any oxidation process, the temperature is coming through what parameter? Through the constants V by A and B. Linear rate constant or parabolic rate constant, those two constant, those expressions, if you look into in detail, then you will find that those two parameters will depend strongly on the temperature. And that means at different temperature, the B by A and B values changes, and for that reason the thickness of the silicon dioxide will also change, it will increase. And this curve is for 100 silicon, and its substrate is substrate resistivity is 3 to 10 ohm centimeter. That means when you will record some data in oxidation versus temperature, or the oxidation means oxide thickness versus temperature, or oxide thickness versus time, always you have to mention the substrate orientation, because we have seen that the substrate the oxidation process is dependent on the substrate orientation also, and at the same time you have to mention that the resistivity, I mean that will tell you, give you the information regarding the doping concentration. If the doping concentration is very high, the resistivity is low, and later on we will see that the oxidation process is also dependent on the doping concentration. A highly doped region and very low doped region, the oxidation growth rate are not same. It's different. That we will see in the next slide. Another curve it is shown, that is this reaction rate constant, that is the B. As I told you that the parabolic rate constant is dependent on temperature, linear rate constant is dependent mainly on the surface reaction rate constant, that is also dependent on temperature. And here the parabolic rate constant is the diffusion process, because it depends on D, capital D, and the capital D is what? Diffusion constant, and this diffusion constant is a strongly function of temperature. Parabolic rate constant is dependent on the D n star by Nv. So that D is the diffusion constant, and it is a strongly function of temperature. So parabolic rate constant changes with temperature, and because of that you can see that oxide growth rate also increases and thickness increases. Now at different ambient reaction chamber ambient pressure in a pyrogen steam oxidation, either it is 100 or 111, with temperature, because the temperature increases here, you see this side it is increases, and bottom scale is 1000 divided by T in Kelvin. But if you increase the temperature from, say, here is 500, so 1000 to here is 1100 degree centigrade, then we have seen that parabolic rate constant increases. This is the parabolic rate constant B, and its unit is micron square per inch. Okay. So that means the parabolic rate constant dependence on temperature, and at the same time the oxide thickness dependence on temperature is shown here. The first curve, the reason is explained in the second curve. Because if you go on changing the temperature, the B increases, so automatically the oxide thickness will also increase for a certain temperature. Next. So now doping dependence effect we will study. Doping dependence effects. So doping dependence effect, there are two doping dependent effects. One is the type of dopant, another is the concentration of dopants. Type of dopants are namely whether it is a p-type dopant or n-type dopant. That means where impurities are boron or impurities are phosphorus or antimony or arsenic, like that. So that is the type of dopant. So this oxidation growth process depends on the dopants, what type of dopants you are using, and second, what are the doping concentrations. The both factors decides the oxidation growth rate. First, let us concentrate on the amount of doping level. It has been observed that heavily doped silicon oxidizes at a faster rate than lightly doped material. Let us try to understand this point little bit in detail. If you remember the cross section view of the silicon process, wafer processing, then after emitter diffusion has been done in case of bipolar process, then what is the next stage? Next stage is the contact window formation, and for that you are going to have some oxide layer over the entire surface of silicon material, silicon crystal. So now there at the surface, some region are the emitter and some region are the base and some region are the collector. So for example, if you look a region like this, for example here a surface, this is a emitter is a N plus, then this is the base is a P, and here is a deep collector. If you remember that deep collector is a N plus. So now here is a buried layer, So now it reaches here. Now you see, if you remember this structure like this, so now you see here, now if you grow a oxide here on the bare silicon surface like this, so some region it is N plus and some region you are getting the P and some region also N you can get. So this is N plus. Now here the dopants are phosphorus P and concentration is high concentration. Sorry, dopants is phosphorus pH and high concentration. Here the dopants is p-type dopant, means it is a boron B and concentration is moderate concentration, and again here high concentration. That means this is a practical situation where on the silicon surface some region the concentration is more and some region concentration is less, and the highly concentration region the oxidation rate faster. That means what will happen? In this region the silicon dioxide will grow at a faster rate compared to this region. So as a result of which, at a same temperature and same time, if you grow silicon dioxide, then what will happen? The silicon dioxide here will be small and this is N. So here it will be small, here it will little bit more, then what will happen? Again here is small, then here it is little bit more, then again here is small, like this. Then at the surface you are not going to have uniform thickness of silicon dioxide. So this is really a problem. And now this particular problem can pose some other difficulties. For example, because of this doping dependence effects, when you are going to have metal pattern on the surface of the silicon, then if the silicon surface is not smooth enough, there are some sort of like this, somewhere thickness is small, somewhere thickness is large, like that. So there is a chance of discontinuity of the metal lines, because much irregular surface, the probability of discontinuity of the metal lines will be higher. This doping dependence effect has given some advantages also. For example, if you remember the buried layer formation, buried layer is very highly doped region, and after buried layer formation, if you go for the buried layer formation, then you are going for a drive-in process, means you are going to increase the thickness of the diffuse region. For a long time you are sintering the buried layer, that is drive-in process. So during that time, small oxygen is also introduced into the sintering, into the drive-in tube. So there the oxide will grow, at the same time the drive-in process. So then the buried layer portion, the oxide thickness will be more compared to the other region. So now there oxide thickness is more, means it will consume much more silicon compared to the other places. So as a result of which, if you remove the oxide later on, then in the buried layer region that you will get a very small group, just like this. This is a buried layer. This is N plus region, and in this N plus region, so oxide thickness is more. Then after that you are going to grow the epitaxial layer. So in the epitaxial layer, before going for epitaxial layer, this is AP. So this is AP. So before going the epitaxial layer, all the oxides are removed. If you remove, so since here oxide thickness is more, so it has already consumed more silicon. So that means here you will find a group here, small group, and that small group will help you in the further alignment process. As you are growing epitaxial layer on silicon surface, then in the subsequent process, how can you see where is buried layer? Because inside the buried layer, again you have to grow the deep collector or the extrinsic base or base, emitter, etc. You are going there, isn't it? This base you are going to align inside the buried layer, and the emitter you are aligning inside the base. So the subsequent alignment process, you have to identify the location of the buried layer. So now if the small groove is there, if you grow epitaxial layer over and above, that means in the buried layer region, that depression, the periphery depression like that, that is a 3D, this is a cross sectional view, and if you see the planar view, there also you will see some depression is there, and that periphery mark of the buried layer will follow in the subsequent steps, and that will help you to align the further steps. So that is one advantage there. But in case of metallization scheme or metallization program, so there it may create problem. Next is considerable difference in oxide growth behavior has been seen in boron and phosphorus doped material. That is another thing. That means this not only the doping amount, the level of dopant concentration, but also the type of dopant. Either it is a p-type dopant or n-type dopant, depends on that the oxide growth rate also varies. In case of VLSI N plus P N transistors, there is a need for thin oxide which grows in the linear region. What I discussed till now, that is written here. You see in the slide that the oxide growth rate of emitter can be as much as 2 to 5 times faster than that of the neighboring regions where the doping is light. That means in the base region. In the emitter region, here the oxide growth rate is faster because there the doping concentration is very high. As a result, steps will be formed in the oxide with the possibility of breaks in the metal interconnection. Just now what I discussed. Next, in a diffusion limited oxide growth region, the growth variation is not a problem, because there you are going very large oxide thickness. There, if say 1%, 2% growth variation may not create problem. But when you are going for very thin region, that means that is not diffusion limited oxide growth region, that is linear oxide growth region. So there growth variation is really a problem. Next, we will define one parameter which is known as segregation coefficient. Just now I told you that the oxide growth depends on the type of dopants, but I have not mentioned the reason. The reason is coming from the segregation coefficient of the different type of dopants. The segregation coefficient is defined as the impurity concentration in silicon by impurity concentration in silicon dioxide. So it is known as M here. The M is nothing but the ratio of impurity concentration in silicon to that in silicon dioxide. That is the segregation coefficient. Now we will see for boron, M is less than 1. So if M is less than 1, then what happens? You see, M is less than 1 from this expression. That means the impurity concentration in silicon dioxide will be more than in silicon. That is that's why M is less than 1. Impurity concentration in oxide will be the more in case of boron. That means boron atoms try to be in oxide more compared to that in silicon. As a result, what will happen? Bond structure of the silica film weakens, because in the silica film in silicon dioxide, whatever was there, so there if lot of boron atoms trying to stay inside the bond structure of silica film, so that bond structure will be weak. So because of that, diffusivity of oxidizing species increases through it, because if bond structure is weak, then lot of oxidizing species will diffuse through that silicon dioxide layer. So there is a considerable increase in parabolic rate constant B with little changing linear rate constant in case of boron. So in case of boron, since M is less than 1, impurity will try to stay inside the oxide more compared to that in silicon. As a result, the silicon dioxide bond structure weakens, and so the diffusivity of oxidizing species increases through it. And since the diffusivity changes, so obviously oxide growth rate increases. And as it decided by parabolic rate constant, B is dependent on the diffusion constant. That is the case with boron. Now let us see what is the case with phosphorus. For phosphorus, M is greater than 1, just opposite to that of boron. For phosphorus, M is greater than 1. So, if M is greater than 1, then this relation tells you what relation? The expression for segregation coefficient. So, M is greater than 1 means there we found that impurity concentration in silicon will be more compared to that in silicon dioxide. That means the phosphorus atoms would like to stay in the silicon interface more compared to that in silicon dioxide. As a result, what will happen? There is a little incorporation of phosphorus atoms in glowing oxide, and all the phosphorus atoms piles up at the SiO2 interface. At the interface, in the silicon side, they will pile up, because more and more they want to stay in the silicon. So, as the piling up increases, that will increase the reaction rate. And what reaction rate? That is surface, because surface lot of phosphorus atoms are piled at the interface. So, that means surface property is going to change. So, what surface? Silicon surface. Lot of phosphorus atoms accumulate there. So, that means which parameter will be affected? Surface reaction rate constant parameter will be affected. So, that means there the B by A value will change in case of phosphorus, and parabolic constant will remain insensitive to doping. That means in case of boron, the parabolic rate constant B changes. In case of phosphorus, the linear rate constant B by A changes. Because of these two, attacking of phosphorus and boron dopants is different. One attacks the B, another attacks B by A. So, growth rate increase is different, growth rate change or growth behavior is different in case of phosphorus than in boron. So, that is the reason. Okay? And with the concentration, the growth changes. What is the reason behind it? Because if the doping concentration in silicon is more, that is independent of boron or phosphorus. In case of boron as well as phosphorus, if the substrate is having a higher concentration of impurity, growth rate is faster. As I mentioned, the 2 to 5 times faster in emitter, because it is highly doped region. So, there lot of impurity atoms in the silicon means there the silicon structure weakens. So, because of that the growth rate is more and more. So, that is the reason of the doping dependence effect. Now, next see effect of impurity and damages on oxide rate. Effect of impurity and damage. So, impurity already I discussed. Now, let us see damage. So, water is another impurity moisture. So, a significant acceleration in the oxidation rate was observed if moisture level rises from less than 1 ppm to 15 ppm. Then sodium is another contamination normally available in water, or it comes from the furnace chamber. So, it has been observed that high concentration of sodium influence the oxidation rate by changing the bond structure in the oxide, thereby enhancing the diffusion of oxygen molecules in the oxide. These are impurities, undesired impurities. In earlier slide, we have discussed on desired impurities in boron and phosphorus, etc. Those are intentionally incorporated to change the conductivity of the silicon. But here, the impurities are undesired but unavoidable. Those will be there to a small extent, that is water molecules and sodium. Okay. Next, halogen. We discussed on water molecules, on sodium, then halogen molecules. And halogen molecules are mainly, we are concerned here, the chlorine atom. Certain halogen species improves both the oxide and underlying sodium properties. It reduces sodium ion contamination, increases dielectric breakdown strength, and reduces interface trap density. It has been observed that 1 to 5% HCl increases the die oxidation rate. So here one important point I would like to mention is that if little amount of chlorine is introduced during the oxidation process, particularly dry oxidation, then what will happen? If there is a sodium contamination, that sodium and chlorine will react together and will form sodium chloride, and which will not remain as an ion. As a result of which, what will happen? The oxide dielectric breakdown strength will improve, because if in the thin oxide some ions are available and those ions are charged particles, and in case of MOS gate oxide they will affect the threshold voltages and other. So that is why sometimes we intentionally incorporate small amount of chlorine containing gases, and which normally we use TCE, trichloroethylene. So that will help to remove the ions inside the oxide. And interface trap density also reduces. Next point, let us see damages. Separating damage effects and dopant effects on oxide rate is difficult. The enhancement of oxidation rate due to damages is seen in case of argon implanted silicon. Sometimes some implantation steps is followed in some VLSI process. So because of implantation, and if it is a high energy implantation, then crystal is going to be damaged little bit, and this damages enhances the oxidation growth rate, because if the silicon crystal is damaged, the bond structure weakens, whether it is in oxide or it is in silicon. If bond structure weakens, then the parabolic growth constant B will change, because lot of oxidation species can go through that weak structures. So the oxidation growth rate enhances. So these are the effects on damage. But the thing is that dopant effects and damage effects, how do you separate? That is very difficult. But if before oxidation, if you implant some argon ions or argon atoms into the silicon, then after that if you go for oxidation, it has been observed that oxidation rate is enhanced, means oxide thickness is more. That is because of the damaging of silicon layer. Orientation dependent effect. And earlier some curves we have shown that the growth rate is dependent on the crystallographic orientation of the substrate. It has been found that parabolic growth rate B has been found to depend independent of crystal orientation during oxidation. The linear rate B by A, on the other hand, is related to the rate of incorporation of silicon atoms into the silica network. These are the effect on the parabolic growth rate constant and linear rate constant on crystal orientation. The density of silicon atom on one plane is larger than on 1,0,0 plane. Thus, the B by A, which is the linear rate constant of 111 silicon is larger than that of 100 silicon. In 111 silicon, the silicon atoms are more available on the surface. In comparison to 100. That's why because of available of silicon atom is more, so obviously oxidation will be more, and then oxide thickness of 111 plane is more compared to 100 plane. That also we have seen experimental data come. Okay. The change in B by A, that is the linear rate constant, is 111 is to 100 is equal to 1.68 is to 1. That is the ratio change. This B by A value changes because of what? Because of availability of more silicon atoms in case of 111 crystal. This is the reason of crystallographic orientation dependence effect of silicon dioxide. Another point I would like to mention, the oxide stress. The oxide stress is formed during the growth of silicon. Why? Because silicon and silicon dioxide will have different temperature coefficient of resistance, because those two are different material, and the temperature coefficient, thermal expansion coefficient of silicon and silicon dioxide are different, and that is the thermal oxide growth process is done at higher temperature again. So in that temperature, since expansion coefficient of silicon and silicon dioxides are different, so automatically stress will form, isn't it? When the stress form because of mismatch of thermal expansion coefficient. Here also, because of silicon dioxide both are present at high temperature, they are not their thermal expansion coefficient is not perfectly matched, so stress will be developed, and because of those stresses, so some defects will also appear, and those defects may deteriorate the performance of the device. So that's why when we are taking the silicon and silicon dioxide out of the furnace, taking out, that means unloading, so we have to take care so that the wafer does not experience a temperature shock. Similarly, when we are loading the wafers into the furnace which are kept at higher temperature, we have to see that the temperature shock effect will not be there. Gradual increase of temperature, and when you are taking out the wafers from the furnace, the slowly you have to take out so that the thermal shock can be avoided. Suddenly if you take out, so inside the furnace temperature is 1000 and outside the furnace room temperature say 20 or 25 degrees centigrade, so sudden change of temperature, so the contraction will take place, and the contraction will not in the same fashion of silicon and silicon dioxide, so automatically a stress will be developed, and because of that some micro cracks will be formed, and those micro crack may damage the entire silicon wafer. So this oxide stress is a very important point we have to consider in process steps, in different process steps. High stress levels can contribute to wafer wrappage, film cracking, and defects formation in underlying silicon. Just now I told. Next, room temperature measurements after the thermal oxidation of silicon show silicon dioxide to be in a state of compression on the surface. silicon dioxide will be in the state of compression. Stress values of 3 into 10 to the power 9 dynes per centimeter square are reported due to the difference in thermal expansion coefficient of silicon and silicon dioxide. This is the stress value, and that stress is compression stress. Stress can form structural damage in the underlying silicon, which results in increase of junction leakage current. The structural damage will increase the junction leakage current. These are the effects of stress. And which is coming because of the thermal expansion coefficient mismatch of silicon and silicon dioxide. Clear? Next slide, I will show a diagnostic tool of silicon dioxide, because once you form the silicon dioxide, then you have to check, or you have to see the quality of the silicon dioxide, how the silicon dioxide quality is characterized. So there are certain parameters you have to tell, or you have to mention regarding the quality. First is the density of the silicon dioxide. Second is the dielectric breakdown field of the silicon dioxide. Third parameter people would like to know is the thickness of the silicon dioxide film. Fourth parameter you have to mention sometime, the refractive index of the silicon dioxide film. The porosity of the silicon dioxide film is measured from the density, and there are several techniques available to measure the density of the silicon dioxide film. But the thickness is another important parameter people would like to know, and that can be measured by several techniques. One such method is known as ellipsometric technique. Ellipsometer is a measurement technique by which you can find the silicon dioxide thickness as well as you can get the refractive index of the film. Other than that, you can have some rough idea of the silicon dioxide thickness, that is from the observation of color of the silicon dioxide film. Silicon dioxide is a transparent film, and depending on the thickness of the silicon dioxide, if you look onto the surface of the silicon dioxide, the color will change for different thickness of silicon dioxide film. From there you can have some rough estimate, and some color charts are available. From their rough estimate always you can make what is the approximate value of the thickness, but the exact measurement is possible with the help of the ellipsometer instrument. And such an instrument basic component is shown in this slide. What is basically done here, a monochromatic light source is here, and that is passed through a collimator lens, and then you will get parallel beam of light, and those light is passed through a polarizer drum, and the polarizer drum polarizes the beam, optical beam, and it is linearly polarized light. And after that, this optical beam passes through a quarter wave plate, which is known as a compensation or compensator. This is a quarter wave plate, and after emerging from the quarter wave plate, this beam, optical beam, will be elliptical polarized. So, the polarizer drum will change the beam to a linearly polarized beam, and then quarter wave plate again changes the polarization, plane of polarization, that is from linear polarized light to elliptical polarized light. Now, after reflection from the silicon dioxide film, here is the device, silicon dioxide top film and the bottom is the silicon. So, after reflection, they again form the linear polarized light, linear polarized beam, and this beam passes through a analyzer drum, and the analyzer drum means the lenses are there. The analyzer drum, if you rotate, then you will be knowing how much the plane of polarization has changed, and after filter, this is connected to a detector, photodetector. The photodetector will detect the intensity of the beam, how much light is coming. So, by changing the polarizer and analyzer drum, you can find certain situation the intensity is minimum, and that intensity is found in extinction meter. So, with this technique, just basic principle is, after the reflection from the silicon dioxide, the change of plane of polarization will take place. How much is the polarization angle changes, plane polarization plane changes. So, that you have to find from the analyzer and polarizer drum rotation. And there are two important parameters. If you find from this analyzer and polarizer drum readings, so from there you can get two important parameter values, which is known as psi and delta. And the four drum readings are A1 and A2 for the analyzer drum, and P1 and P2 for the polarizer drum. And then from those A1, A2 and P1, P2 values, we found the psi and delta. These two are known as ellipsometric parameter. Psi is given by 180 degree minus A2 minus A1 divided by 2, and delta is 360 degree minus P1 plus P2. And once you find the psi and delta, then tables, graphs and computer programs are available to find the film thickness and refractive index of the silicon dioxide layer. So, a rigorous analysis is available, and you can go through that, how the thickness and refractive index are related with this ellipsometric parameters psi and delta. Basically, from the analyzer and polarizer drum readings, we are getting psi and delta. Then we are following certain tables. For different psi delta values, the oxide thickness and refractive index values are given, and you have to see where it matches. For certain refractive index values, for certain thickness, we will see that psi and delta exactly matches, and that is the value of the oxide thickness and refractive index. And computer programs are also available for different layer structures. There also you can feed the data of psi and delta, and you can get directly the exact value of thickness of silicon dioxide and refractive index. That is regarding the thickness and other values. So, next is the oxide trap charges, that you can easily found by forming a capacitor, and you can get the dielectric breakdown strength from standard capacitor, you can measure it. So, in this way the oxide thickness and refractive index can be found, the density can be obtained from porosity idea can be obtained from the density measurements, and dielectric breakdown strength also measured from the capacitance values. Capacitance measurement of oxide will be the insulator, and you form a top metal and bottom metal film, and then measure the capacitance. You go on increasing the voltage when the dielectric breakdown occurs. So, in this way you can get the breakdown field of the dielectric. So, these are the several ways by which the oxide layer is evaluated. Okay, let me stop today.
Let us now show you how the wafers are loaded inside a furnace. You can see a quartz carrier being taken out of the furnace. A wafer is placed vertically on the slot of a carrier. We want to oxidize this wafer at 1000 degrees centigrade. The carrier, along with the wafer, is now being inserted manually in the constant temperature zone. Notice that a quartz pull rod is being used to insert the wafer inside the furnace. In an industrial process, the entire process of loading would be done automatically. Here, in the students' practicing laboratory, we are doing it manually. Notice that the wafer is being inserted very slowly and gradually into the central zone of the furnace. This is absolutely necessary to prevent the wafer from experiencing a thermal shock and getting damaged or cracked. In the central zone of the furnace, we have kept the temperature constant at 1000 degrees centigrade. As soon as the wafer reaches the central zone of the furnace, it becomes red hot. We now close the furnace and keep the wafer inside for a fixed time to grow thermal oxide. Depending upon the required oxide thickness, we vary the oxidation time. After 30 minutes, you can see that the wafer is being taken out very slowly. The temperature of the wafer is allowed to reduce to room temperature. The wafer is taken out. You can determine the thickness of the oxide grown from a color chart because silicon dioxide layer attains distinctive colors at different thicknesses of the oxide. Another method to measure the thickness accurately is by using an ellipsometer.